Well, so in the previous video we proved this theorem, that is it gives a necessary and sufficient condition for a real number alpha to be constructible. And let's just go through the conditions once more. The conditions are that we find finitely many real numbers, these lambda i's, such that the square of the first one of them belongs to the field of rational numbers, and the square of the ith one belongs to the extension of f naught obtained by attaching the previous lambdas for these values of I, and the real number alpha itself belongs to this extension obtained by attaching all the lambdas to the field of rational numbers. So if alpha is constructible, then such numbers can be found satisfying these conditions, and conversely, if we find such numbers for which these conditions are true, then alpha is constructible. So that way these conditions are necessary and sufficient for constructibility. Now let us see what consequences we can derive from this. And the first consequence you will get from these conditions is that we are now in a position to say something about the degree of this extension over f naught. So let's see what that is. Note that the degree of this extension over f naught is this product, where we are of course using one of the results we have already come across in field theory. Namely, you can involve the intermediate extensions in order to express this degree as a product of some other degrees, and those intermediate extensions are these. That is, first we consider the degree of this original extension over this lower extension. Okay, that means you can of course understand what this extension is. Truly speaking, this extension is nothing but the extension of this extension obtained by attaching lambda n to this. That is, this itself is a subfield of the field of real numbers, and if we attach lambda n to this, then that's what this is, that is this thing. So here we are looking at the degree of this over this times, and we can of course carry out this process by then writing the next factor, that is the degree of this over the lower one. Over this one. And it goes like this, and eventually we reach the degree of this over f naught itself, that is the field of rational numbers. Now what can we say about these individual degrees from these conditions? Let's see, actually we can say something. Although we cannot say exactly what the degrees are, but still we can say something. You now look at this condition, lambda I square belongs to this, because you may, you will encounter some intermediate. Let's just consider any arbitrary factor from here. It will look like this. I over this. I minus 1. This is the extension of this field obtained by attaching lambda I to this lower one. And what do we know about lambda I? Lambda I itself may or may not belong to this. That is, lambda I itself may or may not belong to this. We don't know. But we know that lambda I square belongs to this. So, from this condition, we know that lambda I satisfies this quadratic polynomial. And this quadratic polynomial is a polynomial over this field. That means it is coming from this polynomial ring. Because it's a quadratic polynomial, the degree of lambda I is either 1 or 2. It is 2 if lambda I itself does not belong to this field. But if lambda I itself, of course, belongs to this field, then the degree is 1, because in that case, lambda I satisfies this linear polynomial, which in that case becomes a polynomial over this field due to lambda I being an element there. So that means that the degree of this, that means this degree, the degree of this over this is either 1 or 2. That comes from the degree of the polynomial. Okay. So which means that all the degrees that you see here are, each one of them is either 1 or 2. So that tells us that this product in general is a power of 2. So let's write these things systematically. Let's end this thing here, and now let's write these things. Since lambda I, we of course are not going to write all the things elaborately, but we are just going to mention the condition and then write the final conclusion. Because of this, the degree, shall I be able to write it in one line? Let me try. Lambda I over this is 1 or 2. Hence, the degree of this over F naught is 2 to the power r, where r is some non-negative integer, and r of course is less than n, less than or equal to n. We write r because we don't know which one of these factors are equal to 1 and which one are 2. That entirely depends on these specific lambdas, the values of these specific lambdas. But in general, the form of this number is this, it's the power of 2. Okay, so that gives us this corollary, the first corollary to the above theorem. Which is stated like this: if alpha is constructible, then alpha lies in some extension of the field of rational numbers of degree a power of 2, and some extension means this extension, some extension of the field of rational numbers whose degree over the field of rational numbers is a power of 2. And note carefully that this is a necessary condition for constructibility, not a sufficient one, but still it is powerful because it will give rise to another condition which will be very useful to us, that will give us another corollary, degree a power of 2. Okay. Now let's see where we can go from this. So, if alpha is constructible, then by the above corollary, there exists an extension K of F naught, that means the field of rational numbers, and this K is of course that K, this one, such that alpha belongs to K, which comes from the last part of our theorem, and the degree of K over F naught is 2 to the power r for some non-negative integer r. Now, since K is an extension of F naught, K contains F naught as a subfield, because that's just what it means for K to be an extension of F naught. But at the same time, alpha also belongs to K. So K would contain the smallest subfield containing both alpha and F naught, and we already know what that subfield is. In fact, that is the subfield obtained by adjoining alpha to F naught. So because of this and because of this, we have this. This is the smallest subfield containing both F naught, the field of rational numbers, and alpha. But when this happens, we know some result from our first section that tells us something about the degree of F naught alpha over F naught. But then, so what does F naught alpha become? F naught alpha now is a subfield that contains F naught, but at the same time it is contained in K. So that is why the degree of F naught alpha over F naught has to, not only will it be less than or equal to the degree over F naught, but it will have to divide the degree of K over F naught. And this we are getting from the first section. There you will see that in one part of our discussion we have this result. Right after we prove our first result in the first section in field theory, there we have this conclusion. And that time we mentioned also that we are going to use this condition when we apply this thing. So now we are applying. So this means what? This means that the degree of this extension over f naught itself should also be a power of 2. Must be a power of 2 itself. But we already know what this degree is. This is the degree of an irreducible polynomial that alpha satisfies and which is an irreducible polynomial with rational coefficients. So from these things we now have the next corollary. Let me just state all these things. Let me just state the final conclusion from this part of the discussion in yet another way. If alpha is constructible, then alpha satisfies an irreducible polynomial over the field of rational numbers whose degree is a power of 2. Because that degree, that is the degree of the polynomial, is in fact equal to the degree of f naught of alpha over f naught. That we know from our discussion way back in the beginning, where we discussed algebraic elements of an extension. So we are coming from there. So what this corollary 2 says is this: if the real number alpha satisfies an irreducible polynomial over the field of rational numbers whose degree is not a power of 2, then alpha is not constructible. Because if alpha is constructible, then such a polynomial must have its degree equal to a power of 2. But if that is not true, then alpha cannot be constructible. So this is quite a usable condition to prove that some real number is not constructible. This can be used, for example, like this. Say you come across a real number, okay, alpha, and you also find some irreducible polynomial like this, say x cube. I'm not going to write an actual polynomial, but just to get the point across, I'm just writing something like this, say x cube plus a1x square plus a2x plus a3 over the field of rational numbers. That is, it is coming from this polynomial ring, or in our more usual notation, this, that is irreducible, and alpha satisfies this. That means if this is equal to 0, then alpha will not be constructible, because the degree of this polynomial is 3 and 3 is not a power of 2. So that way we can prove that some given concrete real numbers are not constructible, but we of course can use other means to prove that some real numbers are constructible. We will see in the next video on this how these things can be used to actually prove that some concrete things are constructible or are not constructible. That we won't see today, okay, because if I go to that now, then I will have to prove some result first. That will take a long time. Okay, so let's do it in the next field theory video. That means I am going to end the video here itself for tonight. Tomorrow again we have another upload, and tomorrow let's go back to the exercises from Lee. So see you tomorrow with that. Until then, this is me, Lucifer, from a mathematical room. Have a nice night.